Okay, so I'm at Canavan, and I'm going to talk about the ideal integrating bolometer work that's funded through the NASA SIF program. It's very much a collaborative effort with my two very brilliant co-Is, Al Kogut of observational cosmology, and Thomas Stevenson of the Detector Systems branch. Yeah. Okay, our little company's NASA Goddard Space Flight Center. We were founded in '59. We have about an on-site workforce of about 10,000. About a third of those are civil servants. And our primary focus, of course, is a space flight center. We develop missions and instruments primarily for Earth and space science. So I'll talk about the motivation for this work, which the chief motivation right now is in far infrared spectroscopy. We're trying to get extremely sensitive bolometers to allow rapid, background-limited, high-resolution far-IR spectroscopy, particularly of galaxies at cosmic scales. Bolometers, as many of you know, are detectors of radiation, typically in the mid through far IR, that work by converting radiation to heat and measuring a temperature rise. The integrating bolometer concept I'll talk about attempts to circumvent some of the limits on bolometer sensitivity, potentially allowing orders of magnitude improvement. The concept really has three facets. One is a non-dissipative thermometer, which has been previously demonstrated at Goddard. Another is extremely isolating support structure for the absorber pixel, and that's another SIF effort. And finally, a pixel scale superconducting heat switch, which is the primary focus of this work. This is most definitely very low TRL. The uniqueness of this, while macroscopic heat switches do exist, to my knowledge, this will be the first pixel scale microfabricated heat switch. So to give credit where credit is due, this idea was really conceived about 15 years ago by Al Kogut, Harvey Moseley, and Mike DePiro. The real driving motivation, as I had mentioned, is in the far infrared. The far infrared atomic lines are the dominant cooling mechanism for the interstellar medium. In star-forming galaxies, a significant fraction of the total bolometric luminosity is emitted in these lines, especially in the important elements such as carbon, oxygen, and nitrogen. And thus, because these lines are so bright, you can potentially measure the composition of galaxies at cosmic distances. And thus, high-resolution far infrared spectroscopy could provide us with crucial evidence to help us understand galactic evolution. However, this is not easy. It requires very high spectral resolution, and in particular, it requires extremely good detector sensitivity in order to resolve these lines without blending or confusion. So we're really trying to push the detectors to an NEP below 10 to the minus 20, and this would allow cosmological surveys in a reasonable time frame So conventional bolometer, as I said, is a thermal detector. There's an optical absorber that's linked to a thermal sink through a low conductance or low G path. The temperature rise on the absorber is measured typically with a thermometer that dissipates power, such as a transition edge sensor or germanium resistor. For state-of-the-art thermometry, we're able to push the read noise down so that the resolution is really limited by phonon noise, and we're displaying this with a PC, which is going to be a problem. Anyway, the point is that it's proportional to a square root of the conductance G. And so your highest resolution can be achieved by making G extremely small. Unfortunately, G is inexorably linked with the detector's recovery time. And so you can't make G too small, particularly in high radiation environments, or cosmic ray hits will blind your detectors or at least degrade them. And this is a current problem for Planck right now. So with the ideal integrating bolometer, as I said, we use a non-dissipative thermometer to read out the pixel temperature. And so the power onto the absorber is just the photon power. And we put this heat switch in parallel with the thermal path, with the support structure that's holding the pixel. So we have a pixel scale heat switch, and in its on or closed state, the conductance is much higher than that of the structure. In its off state, it has to be less than the conductance. And so you have two time constants, with your off time constant much larger than your on time constant. And this allows you to periodically close the heat switch, dump the heat off the absorber. And this removes the limits on the conductance. You can now push your conductance to much lower values, because any loss of data will just be within one on-off cycle. Also, at the limits of very low G, your temperature rise is basically just the integrated optical power over the on-off cycle time, and you can just measure the temperature at the beginning and end of each cycle, and that gives you the difference gives you the deposited energy. So how do you make a heat switch? Well, to get good conductance, you need a metal, because metals are the only good solid-state conductors at low temperatures. In metals, heat's carried. They're good conductors because they carry heat through electrons. But superconducting metals, below their transition temperature, the electrons get bound into pairs. The pairs condense into a single quantum state and thus have zero entropy and thus carry no heat. So at temperatures far below the critical temperature, the thermal conductivity of metallic superconductors approaches that of dielectric materials like your structure, such as silicon or silicon nitride. On the other hand, you can apply a magnetic field greater than the critical field, and you can break the pair, destroy the superconductivity, and switch the thermal conductivity to the normal state thermal conductivity. And for aluminum, you can get about a factor of 10 to the fifth at 100 millikelvin in your thermal conductivity ratio. So as I said, this is not new. People make superconducting heat switches and macroscopic ones. We do it all the time and use them in our continuous ADR systems, or adiabatic demagnetization systems. What's new here is that we're scaling down to very low, small sizes, and so thin film properties are not very well known. The other thing we have to take into account is the condensation energy, and this is something we'll be studying. So we set up a little experiment, and our experiment is a chip with a couple of what we call pixels on them. The pixels, not really a pixel. It's not a radiation detector, but it does have an isolated island. It's supported by 4 thin legs. It has a couple of resistors on them. One we'll use as a heater, one is a thermometer. One of the legs is a little odd. It's got a thermal link on it, and then this part of it has our heat switch. So I said the island has 2 resistors. One of them will hook up to a superconducting quantum interference device, which is basically just an extremely low noise amplifier that lets us read the Johnson noise and measure the temperature. It's not the fastest thermometer in the world, but if you have a squid available, it's relatively simple and cheap. The island, as I said, is linked through a thermal path, through this thermal link to our heat switch here, which is just a strip of aluminum surrounded by a niobium racetrack coil. And then by driving current through the niobium, we generate a field normal to the aluminum and can drive it normal. So I said one of the key questions we have to investigate is any dissipation we get in the switch. And one of the ways we're going to do this is by using an idea from Carl Rostam, which he calls lab on a chip. What we've done is split the island in 2 and stuck one of our heat switches in between the 2 islands, and made sure the geometry is identical on both sides. And this allows us, since the heat switch is thermally isolated, to easily measure power in it. So plan is to test our device. We'll cool it to below 100 millikelvin with a 2-stage adiabatic demagnetization refrigerator. We will just do a simple conductance measurement, inject heat through one of the resistors, and as I said, use the noise in the other resistor with a squid, which we have right here, to read out the Johnson noise and measure the temperature of the test chip, which is inside this shielded box here that's driven down by the ADR. And of course, we can apply current to the drive coil and switch the switch to the closed state and measure the conductance in both states. We've designed and produced the masks. We've run through our first fab cycle last year. We ran into some adhesion problems, different particular adhesion problems, one at the aluminum gold interface, another at the gold niobium interface. And that prevented us from completing last year. But this year we've modified our design to reduce the number of layers. We've produced the masks. At least the masks are supposed to be here. We've also changed our processes. We've figured out what went wrong, eliminated the problems that caused the lack of adhesion, and we've actually gone through and run process tests to confirm not only good adhesion at these interfaces, but low interface conductance. And these are just a couple of SEMs, one showing a nice clean 2-micron niobium line, and another showing a nice clean 2-micron line that's going over a gold step with no gapping. So the test facility, as you saw in the last picture, we've assembled it. We've operated it down to 70 millikelvin. We've tested the squid, and currently we are reading out noise temperatures using a resistor from an old chip that we had. So this little effort is part of a much larger effort to produce IIB and in the long run to do far-IR spectroscopy. As I mentioned, another part of this, and that's ongoing right now, that's funded through SIF also, is to produce ultra-low conductance support structures using a very clever idea some people call phononic crystals. When these two ideas are combined as the next step, we'll be able to produce an ultra-low conductance structure that has a switchable conductance. As I mentioned, Goddard has produced magnetic penetration depth thermometers, but in the context of X-ray microcalorimeters, which have a much larger, heavier absorber, we'd have to update that design to optimize them for IR detection. Once we have those two elements, we could finally combine them to produce the ideal integrating bolometer. And then, of course, once you have you've demonstrated the IIB, the next step, of course, would be to produce IIB arrays. And I said, as this is part of a longer range vision for far-IR spectroscopy, one of the efforts we have going on right now, run by Harvey Moseley, is to build a compact far-infrared spectrometer in a planar device. So if the IIBs give us the extremely good sensitivity that we need, we would combine these with the microspec and produce the compact ultrasensitive spectrometer that we're looking for. There's another effort going on, this one led by Al Kogut also, called Bobcat, to produce a large aperture, lightweight 4 Canavan telescope that can be lifted by a balloon. Once we have the spectrometer, we can use that with the Bobcat concept to finally do measurements with a balloon-borne telescope, far-infrared telescope, and integrated spectrometer. And of course, in the long run, the idea is this would lead to a far-IR spectroscopy survey mission. So my very rough, quick, top-of-the-head estimate to at least take the IIB to TRL3 is given here. And why should NASA, at least, want to invest in this technology? Well, part of NASA's mission is to understand the birth and evolution of the universe, and this is an important part of it. The richness of the far-hour spectrum and its potential wealth of information has been known for some time, but background limited measurements are still not possible at the longer wavelengths. Thus, the IIB effort is an important part of a larger effort and addresses this long-term need. And I should point out that another way of looking at this is that the pixel scale heat switch is an interesting new tool in the toolbox of low temperature detector designers. The conductance has always been a fixed parameter for all thermal detectors, and this will give you dynamic control. So the technology is potentially useful in other types of devices at very low temperature. One possibility is microcalorimeters, although we really haven't looked at that in any detail. And I'll give you our Goddard chief technologist, this point of contact. He'd be able to point you to any of these technologies. And I think if we can skip ahead one more. I'll stop here, but this is just a little advertisement for my branch and my co-IS branch. The detector systems branch produces everything from detectors up to full spaceflight instruments that cover everything from millimeter to cosmic rays. They do particle detectors, MEMS, everything, and we cool it all down. We built spaceflight millikelvin systems. Any questions? Okay.